This is a review of Chapter 6, the DC to AC converters. These converters are often known as inverters. This is for course EL 4242 on power electronics. Let us consider a half-bridge inverter. What is a half-bridge inverter? You have a one switch here, another switch there. There is a freewheeling diode. There are some capacitors C1 and C2 to split the voltage between the VC between the two C1 and C2, so that the capacitor voltage will be half and half. What we expect that if you turn on the switch, at Q1, then we have a voltage between positive and then positive voltage, and then Vs by 2, and then on the other half cycle, then if you turn on the Q2, then voltage will be opposite direction. You're going to have positive voltage and negative voltage. Now that's what happened. That what we expect, the current through this Q1, the first transistor will be 2 Vs by 2R, and the other one will be R. And now what will happen then when you drive this transistor Q1 and Q2, 180% of the time you have a gate pulse to Q1 and the another one to Q2. And then what we expect that if you have a inductive load, if you got an inductive load, the current will be delayed. If this is your voltage, the inductive load, the current will be delayed, which would be delayed depending on the power factor of the RL you have. And then this would be the current, the voltage will be like a square wave, positive, negative, but this the voltage will be square wave, positive to negative, but the inductor will be pretty much the sinusoidal waveform, although it may have some ripples there. Now what happened that the output voltage, the average output voltage will be Vs by 2, and this then this is the half of that, because the positive and negative RMS value will be like this. But the question is the fundamental component of that, that waveform voltage, the fundamental component of that one, how much will be the fundamental, which will be the useful part. The rest of the will be the harmonics. The fundamental component, RMS fundamental component, 45% of the VS. Like the output RMS value will be, if this is your 100 volts, if this is 100 volts, this will be 50 volts. This will be 45 volts, will be the fundamental component there. But one of the things to remember, if you have a very highly inductive load, then this current will be pretty much will be like a ramping, going from positive to negative, and then this will be the time, the maximum will be Vs by 4FL, the peak to peak, but this is the interval of time will be Q1, the diode will be on, the Q1 will be on, the Q1 will be on, D2 will be the on, and this will be Q2, a Q2 and a D1 there. What it basically happens that if you have the inductive load, this will go from the supply to this Q1 to the load, and the current will rise. And when you turn it off, when you turn off this Q1, then the current has to go through that. The current has to continue this forward direction. What will happen that from the previous cycle, the D2 will conduct the Q1 and D2, Q2, D1. Like this positive one there and the negative one there, but the total energy or the total volt time on the positive and negative should be the same there. That means that we expect that for a highly inductive load, that will be a triangular wave. The current will be a triangular wave. Like if you got a single phase bridge, one bridge will be like the 4 transistors. You have the Q1, Q2, Q3, Q4. You turn on Q1, you turn on Q1, and then Q1, and then Q2, and then turn on Q2. With respect to that, respect to the zero, with respect to the zero, this will be in a positive, negative, half and half of that. But the between the A to B, it will be the Vs. If you turn on the 1 and 2, the whole Vs will appear across the load, and the 3 and 4 the opposite direction. Now basically that it will be double what you expect from a half-bridge inverter there. And if you look to the similar example, this is the symbol of Q1, Q1, Q2, D3, D4, and this is the one. This is the positive and the negative there. The RMS output voltage will be Vs, the fundamental component, there will be ripple there, but the fundamental component would be 90%. That means if you got a 100 volts supply, your RMS will be 100, but the fundamental component, which is the useful power, if you're driving a motor or some other load, that will be that 90% of that. Now you can find out the instantaneous current if you have that. If you know that Vs, you know the F, you know the R0, you know the L, and the instantaneous load current will vary in the range of, you can find out, since there is no load there, you can find out that, how much the ripple there, 50% on 50, the current will be something like that. You know the voltage, you know how the current will rise. The current will rise Vs by L, the slope of that. You should be able to carry that, find it out. The instantaneous load current will vary in the range of what will be the range between the minimum to maximum. You're going to vary because you know that Vs, you know the Vs, you know the Vs, you know the L. This is the slope of the line. This will be only 50% of the time. This is if the frequency is 1 kilohertz, that means period is 1 millisecond, then it will be on half a millisecond how much is going to go. How much is going to go. You should be able to do that. Okay, that is the one. The other one, the RMS output voltage will be what? The question asking for the RMS output voltage inverter will be the Vs, which is true. And then the next question asks for that the peak value. The peak value of the fundamental component of this inverter will be, the peak value is 4 Vs by pi. If you do the Fourier series of that waveform, the Fourier analysis of that waveform, and you're going to see this will be 4 Vs by pi. Please check the textbook. There is a derivation for that waveform. The load current. With the RL load, the instantaneous output voltage inverter will be delayed by the instant output. If the voltage, the inductor, if there is an inductive load, RL load, it will be delayed. If whatever the voltage, the current will be delayed. That's the answer, is it will be delayed. If it was this, if the RC load, if the instantaneous output voltage inverter would be ahead, because the capacitor, remember, capacitive current is a positive or instant ahead. That it will be for RC, it will be the ahead of the instantaneous output voltage. And then for the RL load, LC load, you don't know, depending on the values. Depending on the values, it could be delayed. Depending on if the capacity of that inductor, like it is if you got a JXL, the plus 1 over J omega C, which is like G, this will be JXL minus J 1 over omega C. Depends on the value of the L and C relative. It could be, it could be delayed, it could be ahead. Either of them, depending on their values. The total harmonic distortion, you can see the total harmonic distortion is the total harmonic content of the waveform with respect to the fundamentals. And the fundamental, whatever the fundamental, and then the fundamental is the first one, the third, fourth, second, third, fourth, fifth, sixth, all of the infinity, and that is the one, the first, second, also VO2 square, VO3 square, plus VO square 4 square, and then all of them, and take a square root of them, and divided by that fundamental. This is the total harmonic distortion. The total harmonic distortion is a measure of the closeness of shape waveform and the fundamental component. How it is close. If these are 0, these are not, they don't have anything there, it will be the 100% of that. The total harmonic distortion is how much component of that is the harmonic part of that. Is a measure of the closeness shape between the waveform and the fundamental component. The next one is the distortion factor of the waveform. Is how much is distortion factor. That is the effect. The harmonic factor tell you the total amount of harmonic content, but it doesn't say that how effective will be to filter them out. If the higher the frequency, is easy to filter them out, because the capacitor, remember that if you use a capacitor impedance 1 over j omega c. If the frequency is large, the impedance will be, capacitor is small, easy to filter them out. It's a question of how effective will be in using a filter of the second order filter. That's why you bring that the harmonic content divided by the attenuation of the attenuation is divided by n square. The higher the frequency, the better it will be attenuated. That's why the distortion factor is that the VON is the harmonics, the VO2 divided by 2, the second harmonic square, then of them, then you add all of them, then you take all of the square root. That means it's a measure of how effective is that reducing the unwanted harmonic with the second order filter. The distortion factor, therefore, is a measure of the effectiveness in reducing the unwanted harmonic with the second order filter and the filtering effect. Then you can have also three-phase output. This is your gate signal, the three gate signal 1, 2, 3. Then each one is 120 degree phase shifted and 60 degree. This is the first one, and the second one, and the third one, the fourth one, fifth one. You generate a pattern of logic signal with 100 degree on, 100 degree, 80 degree off, and then you just on and off, and then delete by 60 degree because there are 6 of them total, and that's what generate those one and get them. Now you can show, please read through the theory of that one. You can show that the line voltage is about 80% of their supply voltage. Line voltage between the line between A to B, VAB or VBC, VCA, about 80%. Now the fundamental component of the line voltages will be about 80%. It's a better, 81, 77, 78%. Like the phase voltage, if you have a Y connected load, if you got a Y connected load, then you are talking of the phase voltage. The phase voltage between them is about 47%. Because remember that this is divided by root 2. The line voltage divided by root 3, it gives you the phase voltage. And there are the relationship line voltages and the total RMS value of the line voltage, the fundamental component, and the fundamental of that, the phase voltage, the relationship. Now three-phase, the question asks for three-phase rectifier, each transistor will conduct for either of them. Each transistor conduct for, it could conduct for 180 degree, 120 degree, depends on how you do that. Sometimes you do 180 degree, sometimes you could do in 180 degree or 120 degree. There are two types of things you can do, but in generally 120 is preferable. 120 is preferable, but you can do it that way. 180 degree, each transistor conduct for 180 degree or 120 degree. I think you can do 180 degree is more common. And then there's a lobe, either of them you can do. Like three-phase output voltage for each transistor for output conduct for how many degrees? There are 6 of them. Each transistor conduct for transistor pair conduct for 180 degree. One for 6 of them. There are like a pair. There are 6 of them, 6 pair. That will be 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 1. There are 6 of them, 360, it will be 60 degree. But this is normally that one pair. The 2 of them will be 120 degrees. Normal conduction of that is 120 degrees. There are 3 of them, 1, 2, 3, 360 by 3. That's the common one, 120 degree. That is that. Like in previous cases, 120 degrees is more common. The Y connected load, the Y connected load that depend delayed by the line voltage by 130 degree, because if you look through that, if you look through the phase angle, if you got a log angle, if you got a phase there, you got a large phase voltage, the VAN, VBN, VCN, then you got this one, VAN and VBN, BAN minus VNB will give you the VAB, right? Then VN, if you bring it there, right, bring it there, the negative of the VAN, this will be VNV, NV, and then somewhere the in between them will be that, the resultant VAB. That means it will be line to voltage delayed by, it's a delayed, if this is there, it's a delayed there. Line to line voltages will be that it will be, the phase voltage will be delayed with respect to the, it's like this, it's a behind, it's 30 degree. With the Y connected load, the phase voltage will be delayed with respect to the line by 30 degree. That's basically 30 degree. RMS value, of that, you ask you if the DC supply voltage is 100 volts, the RMS line to voltage will be the range of, you ask for calculation, you know that, what RMS value of that VL, you can calculate it out. This is a simple problem. The RMS fundamental component, similarly, if that we mentioned to you, RMS fundamental voltage is about 77%, you should be able to find out. The fundamental component of the RMS will be the range of, you can calculate it out. The RMS value, the line to neutral voltage is the V of the P. Then the line to neutral voltage you can find is about 45%, something like that. You should be able to find out what is that. If the 100 is given, you should be able to calculate out one of them or none of them. Now, the way it is controlling out the pulse width, you can, for a single phase rectifier or three phase rectifier, you can control the output voltage by using some pulse width. By, in this particular case, we have the 120 degree, but what happens if you don't have a 120 degree? You can make it variable output voltage. What you do like this, you got like a triangular waveform like this, and compare with the DC, then you can see that the width of the pulse could be, make it, if you make it to like a top, the DC make the maximum. If this is the 10, if you make this the 10, that will be 180 degree, like it will be 180 degree. But if you make it small, you can make the width vary depending on that. Like this, if you got the gate pulse, one of the pulses is like 120, the other one 120, and then you can 180 degree delayed, or you can make a 90 degree, whatever you want, depending on that, the control you have. It's an adjustment you can have. Compare a carrier signal with a reference signal. And that means the output voltage will be like a pulse here and the negative pulse here. This is for one gating, and the other gating, the output will be opposite of that. That means that you can have an output in this shape, the width could be variable there. That means that if you have a 1 at 25%, the pulse width will be what? If this is a 1 part 25% of that will be a 45 degree. It will be 45 degree, 1/4 of 180, 1/4 of 80, one fourth of 80, like a 25%, it will be 45 degree. Okay, that's the right answer. Like RMS value of the single phase inverter, if you got a single phase inverter, they ask you compare that. It will depend on the modulation. The modulation will be like VM. RMS value, remember the RMS value is the square root of that, the duty cycle. The modulation index is basically duty cycle. How much is that? How much is the percentage of that modulation index? The ratio of that one at AC, the ratio of the A reference to the AC. Modulation index is basically A reference to the AAC. Okay, that's the ratio. If this is this, that vary the duty cycle. That vary the M is basically the duty cycle, and the duty cycle of the pulse or pulse width. That means this will be RMS value will be the root square root of M, whatever the square root of M will be there. The gating signal for a three-phase, if you want a three-phase signal, what you do, or not a single phase even, you not have a square wave. You want to get an output voltage as sinusoidal as possible. Square wave is not a sinusoidal. They have a lot of harmonic content. The idea is to have the reference signal, the sine wave, the carrier signal, the time wave, so that you try to emulate everyone. What you do if you compare that you can see this pulse width will be, the width will be smaller, the width are smaller, larger, middle there will be larger. That's why you want to see that it's a small, little bit wider, the widest and smallest, so that you try to emulate the output as like possible. Then the number one, that sinusoidal component the output will look like a sinusoidal waveform. You have a middle, you got a fatter or larger width. The sun was the area is more there. That's you want a more area, less area. That's the more common sinusoidal pulse modulation. Now, um, this is very important to have that the gate signal generated by comparing carrier signal with this, reference sinusoidal reference signal. You compare a sinusoidal PWM or this, the PWM pulse width modulation is a sinusoidal pulse width modulation. You compare it with this the sinusoidal waveform. The gating signal is generated by comparing this one. Now, what you do, the one pair, the first one you do this one, the first transistor Q1, and then the other one you pair, you do with the negative sign. You compare this one to the negative sign. In the first one you do the positive 1 and 2, and the other with the 2 and 3 is opposite, inverse of that. This is for G1, and this is the opposite of that. Like you do, this is the one for one was for that one, the other one for that one. Okay, this is the one you do for the gating of the first pair is that one. The other one goes the opposite direction of that. That's why that's what it is generated. The gating signal for G4 is generated by comparing the carrier signal with the inverse sine wave. It's not a sine wave, it's the inverse sine wave. The instantaneous output voltage will be basically, one could generate that. It's basically, that's the beauty of that, the power semiconductor devices, that output voltage is basically VS. The difference between that, the gate 1 and gate signal. Whatever the gate signal you drive, this is your gate signal you drive. This is your gate signal for 4. This is the gating signal you generate in the low level electronics level. Then if you have an analog subtraction or digital subtraction, multiply by the instantaneous basis subtracted by that VS, that is your output. This is your function. This is your switching function. This is called the VS. This is your switching function. What is the function of the switch? Is the difference between that. And that's the beauty. Whatever way you want to have your switches they generate, that output will represent that the shape. Whatever the shape of this, the difference you like have that. So the difference you like to have this one, the output will just multiply the decimals in that. This is the beauty of that, the pulse width modulation. Symmetrical output. The output of an inverter symmetrical normally contains odd harmonics. If you got a symmetrical, there, you got a positive and then a negative there, symmetrical there. You don't have that odd harmonics. You have that only, will have this contain the odd harmonics, not this even, like a 2, 4, 6. They will be valid there. Only the first, third, fifth, and so on. So not the 2, 4, 2, 4, and then 6. They will be not existing. Third harmonic component. The eliminated harmonic component from the inverter should be third notches. You can eliminate it. Sometimes you don't want the third harmonic. You don't want the multiple of third. You don't want the third. You don't want any sixth. You don't want any ninth. There are maybe you may have running an inverter at 1 kilohertz. You don't want anything in the third. In third or in third, sixth, ninth. You may have communication signal or other signals you may have. You want to avoid that. That's why you can have these gradient notches. Please look to this book. There are notches, the 3 notches per half cycle. If you get 3 notches, thermonic harmonic will be eliminated. I think that's the end of that, the chapter's review. Thank you. I encourage you again to review that these the videos for this the mathcad files. Just run the mathcad files, and how to do that is there. Thank you.